All right. Hello, everybody. So today we're going to have Per Bergman talking to us about the telecom industry and how it intersects with cross-organizational data collaboration. I've known Per for quite a while now, and through some of our conversations, Per has related to me about how telecom had a number of firsts in tackling hurdles, not only across organizations, but across other governments and globally. And in fact, one could think of the telecom industry as one of the first in cross organizational collaboration, period, not to say data collaboration. I think it's a good precedent and a good use case for us to dig into today. So welcome, Per, and let's go ahead and get started and learn more about this.
Yeah, thanks, Andrew. So this looks like a strange page here. So when I grew up, we had a comic character from the Eastern Europe called Professor Balthasar, and he had a kind of an analog computer where it created a fluid, and then he drops the blue drop, and it will come up with a solution, like a device that solved the problem. And this is the name of one of the projects, was actually named by me for Ericsson, called Balthasar, because it was like a big analog computer and the solution pops out. So that's why. So this session here I will cover, actually, this was quite interesting. The history of the cellular phone system is interesting just in itself, to understand where we are coming from. Then the actual OSS project, what is OSS and what was that project we did, and specifically 8 mechanisms that they actually patented 35 of these at Ericsson, so I'm not sure which one they got, but we supplied 35 patent applications for this project alone. So there's some stuff. This is from the end of the 90s. I still use some of this stuff. It's still applicable, I would say. So it's not like just history. So, and I have also a bit of an intro here. So this is just telecom perspective experiences, but on the top you see my evolution of home computers is all Sinclair CX81 Spectrum. Djupdrace was actually designed by the Spectrum team, but they resigned and started their own company. And Djupdrace is very interesting because it's you program in Forth and not BASIC, which was an eye-opener in the 80s, that it wasn't just BASIC, it was Forth. For me, that was, wow, this is cool, much cooler than BASIC. Forth is quite dead today, but it was important back then. And I had the flagship computers, 2 Sinclair QL. That's the last of Sinclair's machines, and they had a real keyboard. They had wide Ethernet, not Ethernet networks. They have 2 in a network. They had multi-threaded, multi-window operating system, but Amiga and Atari came, they were clearly better. So Sinclair stuff kind of died out there. But still, we're talking 1 kilobyte of RAM to fit code in. It's kind of different. My phone has 256 gigabyte right today. These computers have like 40K. It's just interesting to see how much memory we have today. So telecom, I was one of the first users of Erlang because Ericsson developed Erlang in the end of 80s, early 90s, and it's the first actor language after Simula 67. It has super lightweight threads. You can have 10 million threads on your laptop. No global locking, so applications like WhatsApp uses Erlang, Couchbase, all of them use Erlang inside. It has lots of the features you need to build a distributed system because it came from how to build a phone system. And we got that early on. Then my first consultant project was to build a GSM load generator. So Ericsson didn't know how many people could run on a switch before it died, and it takes about 8 hours to reboot these switches. So they wanted something to load the switch before telling customers how many people can run on it. It actually happened in Denmark. A busload of German tourists came, turned on their phones, and the switch went down. There's only one in Denmark, so no one had mobile connectivity for 8 hours. So this was that, and then the first OSS project, which was to do what they call performance management recording. So when people had problems in a spot, Ericsson sent out a special card with a special $50,000 phone that collected data, but you need an application to say record this phone in that area for 3 hours. They would just go out and drive the car for 3 hours, collect all the data, and we plotted all the radio level data to see what could be the issue here. That was actually quite cool. Then I worked at Elmtel, which has a long history. So Elmtel in Sweden, the phone company was government-owned for many decades, and Ericsson is a private company. So they decided that the government and Ericsson created its own company to build the phone switches. So it was not Ericsson or the other company. It was a company called Elmtel. They built all the phone switches for Ericsson since 1971. And I worked there for the next generation, which was a failure, one of the biggest failures in Swedish software history on the civils market. There was 9 years of development. I was terminated 96. I was in the room when this happened. But lots of the stuff is brought forward into other projects at Ericsson. But we used one of the first to use object-oriented databases, 1992. We ran TV real-time feed in 1992 to a phone network, new language, new hardware, new everything, and that was a bit too much to take. So, and then I did some just classic SMS gateway billing system workflow, just Telecom, Ericsson, Nokia, until this project we're going to talk about today, Baltasar. And the other thing I'd like to point out, I built one of the first commercial Java projects in the Nordic countries for the Swedish weather services. We actually had a map in an applet and got the real forecast. So you can select the region of the Swedish map. It will actually go to the data store and bring up the forecast coming from these Cray computers they had outside of London back then. Then moved to US 2000. I worked with Versant object-oriented database and system, IBM, Amazon, few startups, but it's been blockchain 100% since 2017. And that's where I also met Andrew in Albuquerque. I think it was 2018. And now I actually live an hour north of that in Santa Fe. So we are almost neighbors. So that's my history. Now we go into the cellular history. Is quite interesting. You probably heard these terms 1G, etc. Where is this coming from? So the history starts in 1969, but obviously there has been cellular type systems before 69, but they're being very spotty, like in a country here and there, and not really any standardization. So in 1969, the Nordic countries decided to specify a Nordic mobile telephony system called NMT, where you can go between Norway, Finland, Sweden, Iceland, Denmark, and use your phone in all the countries. There was nothing like that before, not here, not anywhere. And that was released 1981 in Saudi Arabia first, then in the Nordic countries for some reason. And that's called NMT 450 megahertz. And it was actually running in Eastern Siberia until 2021. So that's a span of 40 years. NMT 450 is an analog standard, which means something specific. It means that the voice is FM, like FM radio, narrowband FM. So an analog mobile standard, it's not doing anything with sampling, or it's just like a walkie-talkie. It just does frequency modulation of your voice over the air and plays it back. So it's like a fancy walkie-talkie, really. And one big advantage was, since 450 megahertz, it's quite long reach. So the guys up in the mountain rescue and stuff like NMT 450, it can reach people far away. Obviously, that is not what we have today, because then you can only have 10 subscribers in a city. So NMT is blasting full energy, but you can't have many people on the same frequencies. So it's kind of useless today. No one would do that today. So 91, the first real kind of global standard was released, GSM, and it was never really global because each country has already allocated frequency bands, so you can't have one phone in the whole world. You all know that you have dual phone, and triple phone, and quad phones. It's because you can't just allocate a frequency band in Sweden and hope that will be free in all the countries. The US have other versions, so it's kind of a as global as you can get, I think. And I think the biggest invention NMT did was roaming, which maybe next page will show. So roaming is the idea. If I talk on my phone in a place, how can it find where the other user is? That's roaming. So that's the whole. NMT actually was the first to implement roaming, so it can find the other phone and connect to it. Might be in another country, and how do you do that? Else it's just a walkie-talkie, really. So.
A quick observation. It looks like from 1981 to 91, that's a 10-year span.
Yeah.
Up to that point, major inventions were happening every few years. What happened in that time period? Just everybody coming to consensus on how to move forward, or?
Yeah. So the GSM specification was actually a competition, and it took years. It took Ericsson 4 or 5 years. So every vendor that wanted to affect the GSM standard had to build radio technology and prove that it worked. So it took them probably 5-6 years each. Nokia and Ericsson, maybe Ericsson won, or I'm not sure. But of course, the winner will decide more of the features, and they already have built them, so it was an advantage. So they actually did a real field trial, phone switch, proved that it works, basically. So that's why it takes up to 10 years. I mean, we worked on 4G in the 90s. When did 4G come out for customers? It's still a long span between the prototype and the actual market. 5G we got 2 years ago. 5G was developed 2004. I mean, that's 15 years. So it's kind of a long gap between the standard, the labs, the research, and the market. And all the operators have to upgrade hardware. I mean, AT&T has like 60 to 18,000 base stations. It's not something you just go and switch over. It's a massive investment. So there is already a 10-year cycle.
Okay.
For each standards.
The larger the established market, the longer it takes for you to introduce new technology. Operations.
Let's see. So then we go. Yes, this is an old image I stole from back then. So this is just 2G then. 1G was analog. 2G is the first digital, which I will come to next. So this is a classic. I will not spend too much time here, but you see the green. That's why it's called cellular system. Of course, they don't look like this. So it's a piece of geography that has certain characteristics, which frequencies can be used, how many people, and you have many cells like this. These are just abstractions. But the cells can also be overlapping, underlapping. This is very simplistic. It's much more 3-dimensional or 4-dimensional model over time too. So the cell changes over time, and they are laying over cells, under cells, and the whole art is called cell tuning. How do you get the maximum resources out of your radio investment of all these base stations? So this is classic GSM 2G. You have the mobile station, call it MS, talk to the antenna and the mast with the antenna. And at the bottom of this, you have this thing to the right, which is a radio base station. It's about 7 feet tall, and it has, I think, the radios in the middle, maybe 6 or 7 of those rack units is one radio, and that sits at the bottom of the antenna. So then you have these cells, multiple cells, people talking. They connect to a BSC, which kind of aggregates multiple cells. And this is pure radio data communication, real time, no services here. It's just pure sub-millisecond stuff here. And then it goes higher up. So MSC is the mobile switching center. That's kind of where it all terminates. And then it can connect to another mobile switching center, and eventually to ISD and PSTN, which is the wired network. So this is how you can call from a mobile phone to another phone, and vice versa. So that's how the whole structure is like. And the roaming is this HLR, VLR. So HLR, home location register, is your SIM card basically. So your SIM card is a copy of the information in that database. It's always there. It says what's the subscriber, what's your phone identity, etc. But when you travel, say I go from Santa Fe, turn off my phone, fly to DC, turn on my phone, how does that work? How does it know I'm there? So that's the V, visiting location registry. I have Verizon, it will be pinged at Reagan National Airport. Oh, here's the SIM card with the phone just waking up, so it can go and talk to my HLR saying Per is now in DC, and it will remove me from the register here in this area. So that's how the routing can work. So it asks the HLR where the phone is right now, because the connections are really connections. It has to know the routing all the way to the antenna or the base station controller. So roaming is these two boxes here. And one thing to note that GSM has by design distance restrictions. That's important because you can't pack subscribers into geography if the reach of the phone is too long and too big, because then you will interfere with people further away. So that's why GSM has a very distinct reach in kilometers. You can't go further because they have to plan, so the frequencies in this box here is not interfering with that, but they can all repeat again over here. So that's the whole trick. That's why GSM in the beginning have this tendency to just cut. You just drop the code. It wasn't weaker. It was just like a hard disconnect. It's because of this. Back then they couldn't tune this. So it's important to pack subscribers onto this. You can't have too long distance because then you will interfere with the people further away. So that's a big thing. It's kind of a bit it's counterintuitive, really. You don't want a maximum blast because then not many people can talk on the network. So, and also GSM is circuit switched. That's important for me.
In this graph depiction, how many telecom companies were involved in developing this engineering feat? Strong vendor or
no? So the specification is the specification. Then you can go and build and sell your equipment. There are many American, Japanese, German, Swedish, lots of Siemens, all of them. Alcatel, Lucent, or whoever the name was in Canada, all of them. There are lots of them in the United building this. Not many left today.
And what about the Chinese standards that were appearing maybe 10, 20 years ago? Have those taken off?
No, not at all.
Not at all.
No, because we come to that, like 3GPP and the GSM and the 5G, all the specifications are global. There is no local anything, so everyone has to agree. Of course, you can build your own network out in the woods. People do that. People actually do. It's illegal because you don't have the right to operate a spectrum, but people do open source radio, GNU radio. People actually build base station, and it works because your phone will find the stronger signal. So you can actually build your own GSM network out here. People do that here, but it's 3 people in the forest. So, and it's illegal, of course, but I mean, we can. So I think this is quite global. There is not really much alternative. We get to 5G and 6G later here. So, yeah, circuit switched. So it's important to understand that GSM was developed in the 80s, and the goal was at least as good voice quality that a fixed line has. Everything is about getting voice quality at least as good as your analog phone. Circuit switched means you allocate everything you need from endpoint to endpoint. So even if the network had better capacity, you can never use it's completely static. Either you get connected through or not. And even if you're alone on this thing, you don't get more speed. It's completely synchronous, allocated, that circuit switching. So of course, today we don't have any of that. And just like it's kind of fun things. So my SQL actually have an engine called NDB cluster that is to build the HLR. HLR is one of the most hit key value databases in the world, probably because all communication will hit this HLR. And a friend of mine from college actually built that for MySQL. So it's a highly clustered, fault-tolerant version that can implement an HLR that get many million transactions per second. But it's just a key value lookup. It's not a SQL engine. It's just a cool thing. So.
I didn't know that MySQL entertained such a use case with such high volume.
Yeah, because MySQL is just a platform. You plug in your engine, you can write your own engine. So this is just an engine you install with, like Maria, InnoDB. You can switch out. So this is a Telecom engine for MySQL developed by my friend who is a database PhD from Sweden. It's just cool. I don't know how many use it, but you can use it if you want to. So basically, it's your SIM card, or now we don't have SIM cards. Electronic SIM card is just a extract from this database. So that's the connection from your phone, your subscription. You can have multiple SIM cards, multiple subscriptions on one phone. The HLR is just having a bit more metadata than that. So the SIM card is your identity here, really. So. And this is just super brief. I'm not going to go into much, but here, so GSM actually was developed with a analysis of the voice tract and how voice works. Everything was geared to human voice communication, and there are different ways of doing this, but basically it was a 13-bit range sample at 8 kilohertz. You know, a CD, what's that, 41 or 44, 48. So a CD today has much higher than this had then, but it's good enough to compare with a voice phone, like a fixed phone. This is the same. So that's kind of what GSM had to do. So it doesn't send exact, like, continuous. It takes samples and do lots of processing in the phone, and then it just sends data, and the other end will play it backwards. So you don't really hear the other person's real voice. You hear a mathematical kind of natural prediction algorithm will make it sound like the person, but it's not at all exactly the voice. They're filtering hard and doing lots of stuff, but it's enough for our ears to kind of recognize the voice, but it's not your voice. It's highly processed. And the other thing here is, just to give an idea, so the first GSM 900 megahertz, you can run about 1,000 people in one cell at one time. And how do you do that? You don't have 1,000 radio channels. That's where the whole European TDMA, time division multiple access, came from. In US, you have CDMA, which is different. So TDMA is very simple. Every person, you can be 8 people on one frequency in one cell. Every of the 8 gets half a millisecond to do whatever they want, and it's just cycling through. So this is a highly synchronous machine. We're talking half a millisecond. You do whatever, then the next, and then it repeats those 8. So in 4 milliseconds, about all the 8 have sent something, and then it's time again. So it's highly synchronous. This is a clock really going down on sub-millisecond level. I mean, that's how it works. So many people on the same frequency at the same, but not at the same time, but almost. Because voice, we're talking 20 millisecond samples. It doesn't matter if it's a little delay of 4 milliseconds in there, you won't hear anything. But it's really a discontinuous thing. This is not at all continuous. It's just small bits of information in bursts like this. So CDMA is then code division. So you instead encode information on the same wave instead of after each other. That's what we use today. So you can push much more data, but it would require much more processing power in the phones and switches, because you are not just sending simple data after each other. You're sending one signal with data on top of it. So it combines all the waves to one complex wave. You have to decrypt, so to speak. That's code division. That's more complicated. So GSM was a bit simpler in the beginning. Just now you can send, and just repeats like that. So Okay, so now leave the 2G and go, or yeah, the history up to 4G, just to show the evolution here. So these are color-coded 2G. 2G GSM is the last slide, is the red thing here. Then we have 2.5G blue, 3G bit purple, and 4G green. And you can see, so the reason it's called 2.5G GPRS is it added IP networking. And since that's not the whole phone system, it's just to add like a module. They didn't want to go from 2 to 3, so they said 2.5 then. So 2.5G is GSM with IP packet, like internet communication on top of, or side by side with the classic 2G. That's, you can see that on the blue. It connects with an arrow into the classical 2G. So the blue one will kind of extend the services on your phone to do IP packets. Now that was 2.5G. 3G, and then 3G, the pink one, is just better radio. So it's not really any revolutionary. It's smarter radio, smaller and cheaper. It's not really a big thing with 3G. 4G though has two things that are quite dramatic. So one is what they call multipath or Rayleigh fading. So this is the problem that you have a signal that goes from your phone, and we're talking half millisecond time span. It will bounce on rocks and cars and buildings and tunnels. So how can the receiver understand it's the same signal but copied a few times? It has to understand it's the same signal, it's not a new signal. And that's what they call multipath issues. So the signal takes multiple paths in time, and both sides have to fix that. How do you understand that this signal is one signal but four copies and not another signal? So that caused lots of the congestion in the newer networks, and the 4G did something to fix that. I'm not sure exactly what. So you got better speed in the same spectrum. And also it's completely IP now based. It's no circuit stuff left. So 4G is completely just packet based, like any of our internet or whatever. There is no circuit switching left because they're fast enough to run voice on it, which wasn't the case in 1991. So, and you can see the connectivity. So you often have multiple standards in one cell site. You can have like AT&T shut down their 3G network maybe 2 years ago or something. So these are co-located often, 3G, 4G, because the investment, you can't just turn off everything old and put some new stuff in. So that's why they can coexist. And you see the arrows, the 4G, 2.5G, 3G, 2G can kind of work together to a degree. So it's not like 2G, then all gone, and then 3G, and then 4G, it's mixed. Like, so, because the investments here are multi-billion dollars to build a thing like this in, say, United States. It's not something they pay off in a year or two. So,
and the consumers kind of sees it, the kind of the top layer of this, right? Where the commercials where they say we have the largest 4G network or 5G network. This is what they're talking about, that they're upgraded their infrastructure such that it's available to the customer.
Exactly. And the phone has to follow, of course.
The phone as well.
Yeah, so next diagram is quite interesting. So here's 4G versus 5G, and 5G is really something different than all the other ones. So 1G to 4 or 2G to 4G is kind of an evolution. It's smarter. 5G is absolutely completely different. This is really a big jump, and we have only seen the beginning. So 5G has much more way of pushing in data and code. That's not just, so 4G here is all hard black box from the vendor. You can't do anything. There are some standards, of course. My phone works and your phone works. Those are radio standards from the 90s. But anything inside the data centers and the switches is completely by vendor. There is no open anything. 5G opens up the whole thing. So they have actually both an edge location. You can do edge computing in 5G and inject code here, much closer to the phone or device. And there are places you get half a millisecond latency. For example, Ericsson in Germany put 5G sensors on like what's called the CNC machines that rotate 50,000 RPM with a piece of metal, which you make something. They put a 5G, a sensor and a 5G transmitter on that rotating piece to detect vibrations and stop the machine if it goes out of bounds. So they use a sub-millisecond latency 5G network in the factory. So this is way more than a phone and some data. This is down to the real-time system. So that's why they have the edge locations closer to the phone. You can't put that back somewhere. You have to have it closer out. So that's a 5G thing. And also the actual backends are now containers and Linux and maybe not Docker, but this is stuff we would recognize today. Open standards in here. So they open up the whole thing much more than before. That's kind of new. And there was a press release. This is a week ago, December 4th. So AT&T is have a contract with Ericsson, $14 billion over 5 years to put in what they call Open RAN. So there is an industry standard for these services. So another vendor can plug in their implementation of a service inside the network, which has never been possible in telecom until now. And Ericsson got that deal. Nokia's stock just tanked. Some people think someone will buy Nokia now. So the situation in the US is obviously Chinese companies you can't use their hardware in the US. Ericsson is one of the few that can actually build 5G networks. There's a few of them, but some in China. So that's why they got this deal now from AT&T to put the Open RAN standard services into their 5G network. So eventually, if there is a better implementation, AT&T could go and just technically switch Ericsson's implementation to some other vendor.
Could you give like a few examples of where 5G is in place and it brings forth solutions previously just not possible? I guess.
Like the factory floor. Imagine you have these machines going super high RPM, and you want to detect vibrations and stop it. That's 5G. You cannot do that with some Bluetooth, whatever. You need faster because this can be a millisecond. I have a friend that actually almost died because the machine got loose and it had shatterproof glass. The thing went through the metal piece going 50,000 RPM, got loose and passed his head and got stuck in the wall. So these are real-time systems now in a factory. It's not just a phone. That's one 5G thing you cannot do with 4G at all. No way.
What's your take on the millimeter wave systems that have been discussed, and there's been some backlash regarding health and safety issues?
Yeah, 5G definitely has those issues, I think. So the thing to the leftmost thing is the interesting what you mentioned. So 5G has a much more advanced use of spectrum, so the device would tell how much speed do you need. So if you want a half millisecond, we are talking very high frequency. 5G can go up to 50 gigahertz. I have just 1.0 or 2.1 on my phone, so it has a much wider spectrum. But of course, if you go that high, there will be consequences. This is energy over the air. So that's why it's called wide bandwidth and flexible frame structure. So the devices are many more can actually decide what type of SLA or characteristics they want on the communication. Do they want half a millisecond? Then it's not just a phone, it's something else in a factory. So, and definitely that type of high frequency energy has health impacts, definitely. And there are some investigations showing some people getting affected by that.
Let's say you're in an urban canyon scenario and you want that kind of high bandwidth capability.
Yeah.
I did a back of the envelope calculation a few years ago, and it looked like the base station, the picocell density would have to be extremely high to serve the the use case. Is that
Yes,
correct?
absolutely, yes. I mean, the idea with 3G was that is in the 90s. So 3G was that you have a cell in your room, not just in your whole office. So there will be millions of these small. That might not happen, but so the 3G network elements we were dealing with in the 90s, you can have on the wall. And what happens if you have 1,000 of them in an office? Yeah, of course, it's lots of electricity or magnetic fields or light, I guess, everywhere now. So I'm sure that's not healthy at all, you know. Hard to prove, but certainly it has some impact, I think, you know. Yeah.
So is there a lot of adoption of the higher frequency stuff, or is it
No.
no?
No special. That's the whole idea with 5G. You can have a phone. So I have an iPhone 15 Pro with Verizon. My 5G here in Santa Fe, I don't pay for the highest ultra wideband. I pay for the normal. It has the same frequency as my old 4G. There is no more energy, so it's a bit faster, but it's not dramatic. You need to find a place where they have those services even. You know, the whole infrastructure has to be matched. You can't just have a good phone. It won't work. There's an ultra wideband 5G. I haven't looked at. I'm not going to. I don't need that, but you get more speed here in Santa Fe and Albuquerque, and all big cities have that now. It's a bit more speed, and the battery consumption goes, of course, up too. So, yeah, so I think this is kind of revolutionary. What will happen when other vendors can inject services here using standard like container virtualization, all that stuff we are used to starts to pop up here now, which is new. You know.
That's right.
And 6G, then we don't know so much about 6G. So, yes, what I said. So the problem here is, since you have a wave, you have to keep like a communication going. You cannot have a 50 gigahertz phone. The battery will drain in 2 seconds. So that's why 5G and 6G has to be much more smart about what does he need to do? Just a phone call, 2 gigahertz. The phone battery lasts 14 hours. But if you want 50, you can't have a phone. So that's why the thing can adjust itself to the use case, which was not possible in 4G and the old ones. And 6G, then, of course, very few. It's research. They talk about 2030. We're talking 100 gigahertz up to terahertz band. 5G goes up to 50, so this is much more energy in the air. So I don't know what kind of device can even do stuff with that. but the idea with 6G is that you have this in the middle. You have your devices, but you can have drones and satellites and a mixed set of receivers before it hits the network. That's the idea with 6G. So you can have all these drone networks, low orbit satellite networks, some other technology mesh networks. You talk to that first, then it talks to the kind of combined infrastructure with antenna and the rest. So 6G is much closer to the end, not so much maybe in the middle.
Are there any militaries using these kinds of frequencies at all, or is it just still no?
Yes, so 6G will be a standard. So it's there. Of course, people can build what the hell they want. You know, I mean, people can use other frequency band. I'm sure military uses other ones, but that will never be the standardized global standard. That's just the military application. There are frequency bands you can run without any licenses, and people are doing that today. I mean, with 6G, I mean a specified by 3GPP global standard. So you can't do anything.
I was just curious about the drone use cases, for example.
Yeah.
Drone swarms and that kind of thing, communications along those lines.
Yeah, I mean, it's there. It's just, this is just a way of standardizing it. But we are 6 years from even a standard, maybe. So it will take many more years before we have a 6G network. But the idea is to push to these small devices many of them, like mesh networking, or they call it fog computing too. Very unclear what this is. Research not done, basically. So but that's where we are. So it's like, yeah, right. So that was the history of the telecom. Now we'll get into the OSS. So OSS is the name of all the, basically in the old days, it was two things. OSS is all the software I need to operate the cellular network, everything. Back then, they put customer facing and billing in something called BSS. But normally OSS is everything. So all the software you need to manage the whole thing. If you're like Verizon or T-Mobile or AT&T, you get OSS from Ericsson, OSS from Nokia, etc. to manage the hardware and software and databases. So that's what the term means. An example, you can imagine network inventory, storage provisioning, network configuration, fault management, performance management, billing. I mean, it's all of the services you need to run a network with thousands and thousands of nodes, which should be up and running most of the time. So Ericsson says, so this system doesn't have one SLA, they just laugh at you. What do you mean one SLA? Fault management, it's number one. We want to know if the thing is down because we lose revenue. The rest we don't care about. They will tell you. It's not one SLA. People, it's kind of funny. It's like the history goes a bit backwards. Back then it was like we have 10 SLAs on our system. What do you mean one SLA? 99.999. For what? These guys have to have multiple SLAs because you can't have high SLA on all this. It will cost too much or be impossible. So they say fault management is the most important. We lose revenue if the thing is down. We need to know. The rest, it's kind of interesting. So the situation then 1997 was that Ericsson's OSS for GSM has been around for many years, was a monolithic piece of software running one server Sybase that works fine in Sweden. Back then, 5,000 cells only. A cell had about 300 parameters and 256 relationships. So it's a kind of a big graph, but still not impossible. The problem was then in southern China, where you have a piece of desert. Next 2 years later, is 10 million people living in a city. They will put base stations there to support those users. And then they saw we cannot run that big of a network in the current implementation of OSS, which runs in one. The biggest I heard was Sun Starfire, the biggest machine Sun had. It didn't work. So that's where we came in to do this ask. Then I was actually the only non-Ericsson employee. I snuck in with a friend because it's only 5 people that started this whole thing. So the ask was multiple models, multiple generations hardware, linkage between the models, plug and play, new bases were added out there in the terrain. Digital twin we had, but which NASA started in the 60s, but it wasn't named. So NASA already had digital twins in the 60s. We did this in the 90s, and in the 2010, someone put a name on this. This has been done many, many decades. So we had to do digital twin, two-way network models, both ways, real time. One API, one schema, full distribution, full metadata services. Also grow and shrink automatically when they onboard new base stations or remove them. Also using very low bandwidth because our communication uses the same bandwidth as the traffic, and we can't use lots of bytes on a network because that would take away revenue from people talking on the phone. So this is quite a massive set of requirements, I can say, and multiple SLAs. Then we have different ones. So that was the ask, and our team actually have a map here. So our team this is southern Sweden. So Linköping is the GSM and architecture where we worked, and Gothenburg and this place called Vänersborg, those are cell tuning experts. They have very much input in how this is designed. And Stockholm had the 3G. So us 4 different teams work together. And I lived on this little island here you can't see, and I have to drive. Yeah, you can see it there. Yeah, so I lived on the quay here on this island. I drove for 2 years up to Linköping to work on this. I worked 4-day weeks, but 40 hours or 60 hours, and then off 3 days. So, and the cool thing for Ericsson, they did more war rooms. So we had 2 big rooms with all the people we needed in the same room or the next room. So project management, technical, business domain experts, architecture, design, coding, writers, methodology, all in one place, which was rare for Ericsson. And they also removed requirements on the following the usual processes for Ericsson development, lots of paperwork. So this was more like a startup for 2 years. So that was the starting point. We were 5 people. It grew to maybe, at the end of the project, I moved to the US. It was 1,000 developers.
Yeah, so let me ask you, based on that scenario,
Yeah.
There's a lot of debate around remote working. Do you think with the technical aspirations this high, would it have been possible to have small remote teams achieve what was done?
Yes. I think these 3 or 4 locations was problematic since we actually have to go there. I think that would have been easier. So we might have wanted to talk more to the people in the other locations than do a road trip, which we did. So some more remote back then would have helped us to communicate, not just via paper or emails. But we have to go to Stockholm and Gothenburg to talk to these guys for a week. And that's not always optimal, but that was what we had,
Mm-hmm.
And I would definitely benefit living on this island to not go. This is a 5-hour drive each direction in the winter on rural roads, no snow removed. And, that was an extreme case maybe, but yeah, definitely. And we also have, go ahead.
No, I was just thinking in some ways it's kind of funny that the technology that you were developing, it enabled the underpinnings for everybody else to be remote workers.
Oh yeah, absolutely. Yeah. No, this was a fun, tough, but fun project in that way. And also that this is maybe a Swedish thing or Nordic. We actually had a method team. We don't see that in the US. So we actually had team members that just watched how we work and optimize how we work. So what is a team? How does a team communicate? You can read books. These guys were hired to watch us and tweak our processes. That's quite rare. So they were kind of interviewing, checking things. How are you solving this? How are you communicating? Maybe do this better. There is a tool for that. So there was actually a team doing that. That's kind of cool, actually. I don't think you have this anymore. It costs too much money, but I mean, it's a method team. Yeah, I think that's, and then the actual solution here, so this was I don't know where to start. So we have so we have the Corba. So this was Corba. Then Corba services with some plugins, adapters to the networks, and the different types of networks, 2G, 3G, different adapters. Then an object database, Versant. So that's one installation, but then it's linked, so you can have 50 of these side by side. It's not just one server with this, it's many. So that's the whole idea. The network grows horizontally, so the data is different. But all the APIs and everything are the same, but the model is different. So that's the idea. So you have a model here, I will show it. You have models for the whole thing, whatever it is. Code generators updating metadata and topology services and actual schemas in the database. And the clients would use the topology to find things and also what types, and then a generic API. So you can't have like specific named APIs like 4G base station. It will be just managed object, but the actual model sits in this metadata layer instead. So the client would load the metadata, find the endpoints, and then communicate via a generic API. Because you can't, it's too many combinations to try to make easy to read APIs. It doesn't work. You have 2G, 2.5G, 3G, 4G, and they're linked together. It's just unbelievably complicated to have a fluent type API. So this, I'll show an example how this looks like. But so that's basically the structure, and everything will expand horizontally as the network grows, and that's the trick. You can't run into any like space or time issues. You just start a new server, install the thing, and then you're up and running. So the network in China, no problem at all. So I will come into this. Bus Corba, Java, then we use JMX. We had people from Sun Microsystem come to explain JMX because that was very interesting for us. JMX is like you have set and get events and operations. That's perfect. So we stole some of the ideas from JMX. And let's see, was there any question? Oh, this is actually the front end. So the old switches, the 2G network elements have a big front-end machine written in Pascal that you send the commands to. So we have to do that in these adapters. I will come to that later. Some of these adapters are very complicated with the old style. The new style is easier. I will come to that. So this is a guy loading a tape into this front-end processor of the phone switch. This is not a switch. It's just a preprocessor, which is like a big machine itself. So that's what we have to deal with.
Quick question on this generic API and topology and metadata.
Yeah.
Are you saying that the client, when it first interacts with those two components there, that it can go from 0 to leveraging the APIs that are available without any human interaction? Discovery is all machine driven.
You could. So we had actually, if you know, so the topology will let you find the structure because you might want to talk to a specific base station. You need to know that one. But you can also just say, I want to find all the cells, all the 2G cells you know about without knowing anything about where they live. So you can do both. Like cell planning needs to cross over our servers. They don't care about what's running in my server, your server. Cell planning is the whole country. So you have to jump sideways, and we supported that transparently to go sideways in this diagram without knowing you switch server, so to speak. So it's a distributed graph, which gets continuous updates from the outside world, actually, because it's a digital twin too. This is not trivial. That's why we had 35 patents on this. So these will send updates all the time.
So when you see the current iterations of the current art of the possible and metadata catalogs in the enterprise, you must be a little disappointed.
Yes and no. I mean, I think this was a research project and very, very capital expensive to do all of this from scratch. Today, of course, there are things out there. You wouldn't have to go do this research. But I do agree, it's a bit like the industry has gone back a little bit. It's maybe simpler, but more stupid. You see what I'm saying? I work with lots of different developers, blockchain, and people don't have, like I feel musicians and artists always know their history, what came before. But in this business, it's a bit like, this is a new thing. No, it isn't. So it's a bit of a lack of history and understanding. Sometimes you feel people are reinventing a wheel that actually was invented 20 years ago. Maybe like that, a little bit. See, so then we come to the last section. Is this 8 what I call mechanisms we used? So this is the model-driven architecture, which was OMG came up with in the 90s. So basically just model-driven. So the model back then, I have it here. I actually have one. I found a model somewhere. Yeah, it's just a big XML file with the whole. This is not one model. It's 5, 6 models. So this is what we did. There was nothing else then. It's an XML schema, not schema, DTD at the top. MP DTD. So here we we outline, this is just a little demo model. It's still 3,000 lines of XML or something. Just all the pieces we want to operate with attributes and ranges and delete commands, create commands, relationships, cardinality. We did all of this in an XML file, basically, then. And these we then have a code generator that generates stuff in the topology, metadata, and also the database schemas themselves have to follow that. And this is a diagram I found from 99. So this is from the router community back then. And you probably heard SNMP, MIB, and that stuff. So MIB is managed information base. That's everything. The black dots is the information tree. That's the graph you navigate. And the data is in this managed objects then. This is all from the router community in the 90s. So we don't want to load the whole, it's too much data. So we can search on the black nodes and edges and then go and load data as needed, because these can have 300-400 attributes per object. That's too much. So we implemented this, and this is also spanning multiple machines. So it's not just in one thing. So multiple databases, multiple machines build this big graph actually, because it can have relationships sideways, associations like that.
So the black is like the discovery layer in the
it's a naming space. We use LDAP naming, so they all have unique names. So you can go and search here. There are some of the attributes in here are copied up so you can search better, but you don't want to pull in the whole Southern China network. It will blow up then. So yeah, so search the tree, but you have the data down here. I think I had some example. Yes, talk about Versant. So I actually worked at Versant. That was the first pick. So Versant was an object-oriented database management system built by people from Sybase that felt that the relational database backends were not optimal for object-oriented implementations. So they wanted to do something. They formed Versant in Fremont, Bay Area, 1996, and I worked with them for 6 years actually here. So it's a high-speed networked object database where object can go across the servers transparently. And you will never model, so we can actually have C, C++, Smalltalk back then in Java. It will never touch the backend, and whatever is stored on disk is the same. The trickery happens in the client, and you can also load the whole subgraph in one network call, which is exactly what we need here. So, and Ericsson also needed second source. So if something happened with the company, we have to evaluate. So we picked Objectivity, which was Objectivity, Object Store, and Versant was the three big ones back then. So we actually took the specialists from the two vendors to do like a competition real time. So we gave them a task. You have 4 hours. We run a speed test. So these guys were coding, and they're both equally fast. So problem was that Objectivity was just, there was stuff we didn't like with it, but Objectivity could have worked too. So nowadays, this market is dead. No one uses, I don't know, I guess this database exists. They call Action or something bought this, but no one is really talking about object databases anymore. I mean, we have no SQL, and of course vector databases and column stores, etc., and property graph and knowledge graphs, but no one really has this anymore for some reason. I don't know why.
Yeah, that was actually a topic of conversation on a recent podcast with Dave McComb. He was going through its history. I'll send it to you. Yeah.
And Versant, I actually joined Versant and moved to the US 2000 because I had done this work, and then we worked on the JDO specification and EGB3 specification, and also OSS for Java back then with some microsystems. But that's all. I guess some of that is still with us. Hibernate is similar, but that was cool. And the Access API looks like this. So we have a generic Corba interface definition files, and they are very abstract. So we have like some interface here, manage object. To do a set, you have the name, attributes, and then a session, like you're connected, and then get. So these are very abstract. So there is only this API. It's much bigger, but you don't have any specific. Everything is in the arguments. So I want to set some attributes in this manage object, which can be a base station or whatever it is. So the API is the same, but you have to know the objects and the types, and that comes from the topology and the metadata services. And this is also, we realize some cases it's not enough to do set and get. You want to, so we actually allowed Java code to be compiled and plugged in and called from the API. So I can say on this managed object, I want to run an action with parameters. So we can actually execute Java code in the backend to do something specific. For example, the old switches, you cannot just set two attributes. There is an order, so you can only set this first, and stuff logic like that we could implement this way.
So it's like a plug-in architecture, I guess.
Yeah, so this is JMX, really.
Mm-hmm.
Oh, yeah, so we had to do that. And then the cool thing was the whole two-way adapters, or the digital twin. So we have this network with thousands of base stations. They have their state, and we have our models in our databases. But now reality changes, so they will actually send updates to us, and we have to update our models. But we also changes on our side and have to update the reality. So this is a two-way, almost real-time digital twin of a whole mobile network. And then it depends on the actual network elements, the NEs. So the old ones is what I said is best effort. You can't run a command and roll back. You run a command and it might corrupt stuff you can't undo. While the new ones, the 3G ones, are much more atomic. Set is done, but the old one is more like maybe not. So that's heavy. So this is a command from the old time. It's called, so the commands look like this, CA, CLP. So this will give you time and date. So it's kind of cool. It's like old IBM 3270 type. You give a command, it will give you back. This is time, the types of all the data. So time command, you have date and time, summertime or not, the day and that matches the actual data here. So it's kind of self-describing. This is the date, this is the time, not summertime, Wednesday. So we have to parse all of this now from the switch. So these adapters were quite complicated. You needed telecom specialists to do this parsing. So this was a big, and sometimes it's way out of sync. You can actually manually say, forget my model, get everything from the network. It's called adjust. It can get so out of whack, so you need to just say start over. So we had to do this. Mm-hmm. Yeah, so that's the two-way adapters. Oh. And then the trickiest part is, so you have all the models in your databases, they're up in sync, but that's what's called a valid configuration still is. So valid configuration is my map of reality as good as I know it. But that's not how Telecom works at all, because you want to say, like this example here, on a Saturday, why would I spend radio resources in an office area where no one is working in the weekend? So this was even in the 90s, they want to readjust and tune the radio network on a daily basis. So Saturday, no one is in the offices. We want those radio resources to go to town, or there's a soccer game or football game. So how do you do that? Yeah, they have to sit and do cell planning. This thing, you just create a future plan, which is a copy on right of the big graph. So we would take reality, and we'll say, This is not a state change that should happen now. We will just collect that under another name called a plan configuration. That might be 5,000 changes, but they are not active. And then the scheduler just pushes out these updates Saturday 3 a.m. and the network changes. This is an extremely valuable feature because so we are mixing the actual state with the future state and can run all the cell tuning on it. It doesn't understand that. I'm just saying, I want to see the world next week and see if there's any issues ahead of time. And they can tweak how much they want. It's still just a plan. And then they can roll out the plan, which is sending 5,000 command transactions to the network. So it in the Saturday morning, no radio in the office, but more radio in the town. And then Monday night or Monday morning, they do the same opposite. This is not trivial. So you have a distributed graph with copy and write. So we don't copy stuff you don't need. This was probably the most complicated thing we needed to do. It has to understand, I'm not reading the current state, I'm reading a modified state, and then it jumps back to the current. So if I just do one change on the big graph, it will just have a little delta. But it has to understand it should go and read my change and not the real one. So we're kind of shadowing state here. So this one was quite complicated, but it's the most useful feature actually. And there was actually, still is, a relational database called Mimer. I think that might exist. It had this feature. It was very cool actually. So you can have a relational database production system. You read from production, but the update can go to a shadow database. And if you read again, it will read the shadow first. So we actually did this in nuclear plant. We actually read live production data, updated the shadow, but then it reads the shadow first. So you don't need to do this, the copy production and restore. You read live data, but you don't update. That was kind of what we actually did here. But this Mimer actually had that built in as a feature. That was kind of cool.
That's cool.
I think it might exist. I have only 3 slides there. So this is just topology, nothing strange. We use LDAP clusters because LDAP is good at, we only had read-only data after deployment. So we deployed all these models. Then you can easily have lots of read-only replicas to get fast access to the topology. So they will look like this. I want to find mod PLN and model version 1, some cell, and then it will give you like the endpoint you need to connect to if you want direct access to that data. It gives you the URL and then also all the attributes for a cell. That was all in LDAP, which is good at that type of read-only information mostly. So that, and then hoppers. So this solves the problem if you go back here. So the hopper is a thing, this is not so complicated today. It's a proxy just saying I'm continuing somewhere else, and if you get from the other direction, it understands it can hop between servers. So we just call them hoppers. So it was a relationship that was a proxy, so it can jump. So the cell tuning guys didn't have to know that we had 20 servers. It looks like one big data set, but we have to implement. So if they do a get or a search, it will search across the relationships, across the machines. So this was the pattern. Yeah. 1 slide and 3 minutes. So use cases. So we built this POC first and showed to 250 plus Ericsson executives, and then got the green light to actually do production. And the first release was 2000. And it was used at least 2011, probably longer, because this architecture is very flexible in that way. But I moved here, so I don't know so much exactly. I know the Portugal's, one of the utility companies wanted to use this because electric grid, what's that? Modules, plugins, and adapters. The rest could work the same. It's just a different plugin, a different adapter, different model, but the software should work the same. Yeah, I think that was it.
Second to the last bullet, you said to manage existing infrastructure. What do you mean by that?
Oh, sorry, I didn't mean to close. Yeah, so I meant that we actually did this. since the software for this ran on Sun Microsystems machines, someone said, but why don't we model those themselves with the same framework, which we did. It's just the adapter is like FTP and licensing, and there's software and a software version. But so the model is different, adapters are different. So we actually installed the actual OSS using the OSS. But the models are different. It will say Sun Machine 1, Sun Machine 2, put the database. So that's what Kubernetes and these guys do today. Declarative saying, I want this service to run on that box. We kind of did that not so elegantly back then for the actual software itself. So we reused the whole framework one time.
So it orchestrated itself.
Yes, yes.
Wow. Yeah, that's interesting.
Problem was, of course, if there was some special case you have to bootstrap. If there is like a hot fix or something, some bugs, we needed to hack this. But technically it worked. So we can say database software related to some server, etc. So we have a whole relationship diagram. The adapters would do scopy or FTP and not telecom stuff, but the whole thing we could use for this other purpose then, to build the resources, the actual software that would then manage the telecom network.
Yeah, that was excellent and thorough, Per. Thank you very much.
Yeah, no, this was fun to
Yeah.
go back to history. I didn't know some of this stuff. Like, oh, that's how it works. I didn't remember that. So,
And I think that many people who watch this later on will have their own internal mapping of, like, you know, how did their own tech industry evolve and what can we learn from this? I think that's the big takeaway for me, is that a lot of the things that we, as you say, reinvent or have yet to reinvent,
yes,
were thought of in the telecom progression here. So
yeah.
that's interesting. So given all that you know about this evolution, what is the one thing that you think we could learn from this as it applies to the current state of cloud structure, et cetera? What is it that you see like we really need to borrow from telecom? Thoughts on that?
So telecom, so this project was a bit ahead of its time, but that was not a common operating pattern in telecoms. I think this project was a bit specific. So I think in general, telecom has lagged behind 5G when they talk about virtualization and open standards here. So they are actually behind. This specific project might not have been behind, but one thing I still believe, it's model driven. I know people say that's old school. I think that was very useful to go back a little bit to this model driven code generator stuff and not be so explicit, to write the simplest possible. It's not always the best, but that's the trend, you know. Can you model things with a model and not hard code everything everywhere? I think, but some people would say, no, that's bullshit. We don't do that.
I think you have some fans in that comment. Model.
Yeah, but some people would just, no, we need an API with 5 operations. We build it here now. They're called ABCD. We don't care. Okay.
Yeah, certainly agree. Like that comment. I'm sure many will, especially those that regularly frequent this.
The group. Yes.
Yeah.
Oh, I need to jump on my call, but this was fun. I hope this was useful for, you know.
Oh yeah, for sure. Hey, thanks a lot, Per. Talk to you later. And again, thank you.
Absolutely. Have a good one.
Right. I'll see you.